I think we should probably get started so the afternoon doesn't get away much, but I'm very pleased to introduce you to Dr. Irina Biktasheva. And Irina holds a lectureship at the moment in computer science at the University of Liverpool, and she's also held or holds a fellowship. You still hold a fellowship at Exeter? Or
Yes, yes.
So she also holds a joint fellowship at Exeter University and spends quite a bit of time commuting backwards and forwards between the two of them. Her husband is actually at Exeter as well, so that makes her a part of that. So Irina obtained her master's degree in physics from the Tomsk State University in Siberia. It was in ballistics or rocket science.
Yes, a long time ago.
And then she moved on from there to the Soviet Academy of Sciences in Moscow, where she developed her interest in spiral waves. And then in the early 1990s, she immigrated to the United Kingdom and obtained her PhD at the University of Leeds, and interestingly enough, at the same time was awarded the equivalent of a PhD from the Moscow Academy of Sciences for her published research that she had done while there earlier. So at the University of Liverpool, Irina teaches in a number of areas, including neural networks and genetic algorithms, computational biology and medicine, and software development and data mining. And she's published many theoretical and practical studies investigating the foundation for spiral waves and their dynamics, and that's what she's going to address. She'll address up to us on that field today. She's also the lead investigator in the Beatbox computational software project, which enables HPC computational modeling of cardiac electrical activity. And she's only visiting the ABI for this week, while on her way back from the physio meeting in Seoul. She's taking as much time as possible to talk to researchers here at the ABI and other parts of the university with similar interests. So she has a few open slots in her schedule. If you'd like to speak to her, please see her after this meeting today, and she can schedule you in for a talk. So thank you very much, Irina. Welcome to Auckland.
Thank you for the introduction, Mark. I'm really pleased to give you my talk here in Auckland, I hope, despite of being quite loaded mathematically, it's still my talk is going to be entertaining for you, and you probably will see some familiar physics there, and I hope you will develop a new point of view at the cardiac reentry and its interaction with a variety of perturbations. That is my aim and the main goal today, okay? So, and if you see any connections with what you are doing here right now and maybe in future, I'm open for all your questions and discussions, okay? So, wave-particle duality of dissipative vortices and implications for cardiology. So, as I mentioned in my abstract, spiral waves are observed in a variety of spatially extended dissipative media of physical, chemical, and biological nature, where the spiral waves re-entry act as organizing centers for regimes of self-organization or transition to chaos. And here you can see spiral waves registered in liquid crystals, in lasers, nonlinear lasers, in catalytic CO oxidation, rusting of steel. That is rocket solid fuel combustion, rotating waves, and even in star formation galaxies. As well as spread of depression in the brain, calcium waves in all sides, social amyloid signaling, Belousov-Zhabotinsky reaction medium, and of course the main motivation for studying re-entries or spiral waves since 40s, I believe, for the last century, was cardiac re-entry and better control of cardiac re-entry in the heart. Of course, the underlying physics, chemistry and biophysics is different in all these processes and has to be appreciated and explained in the first place. However, the common feature of all these phenomena is that they can be described with various degrees of accuracy by reaction diffusion partial differential equations, with solution in the form of the spiral wave rotating around the center of rotation R with angular velocity omega and initial fiducial phase phi. In 3D, it will be not a spiral, it will be really a tornado, so vortex rotating around the filament, like here, and synchronized by the filament. So the initiation of re-entry is not due to the properties of the medium. It is dictated just by the initial condition where it happened. Okay, and a homogeneous system may spontaneously divide into the core and the periphery, synchronized by the signals coming from the core being either the center of rotation or the filament of the vortex. So, subject to a small perturbation, a spiral wave will preserve its pattern and slowly change the location of the core and the initial phase, the frequency of rotation. So it may develop scroll turbulence due to negative filament tension. And the well-known phenomena is drift of the spiral waves, due to the inhomogeneity in the media. So here one part of the media has slightly different parameters than the other part, and orbiting localized inhomogeneity, like here. So steadily rotating spiral. Now the green spot, localized inhomogeneity, and spiral tip goes into orbiting the localized inhomogeneity. Okay? Okay. So there is mathematical explanation now. Why does it happen? And explanation is macroscopic dissipative wave-particle duality. And I hope that will be popular introduction by Professor Dwight Barkley of Warwick University. Okay, so the asymptotic theory presumes that subject to small perturbation h, the spiral wave solution remains approximately the same. However, the center of rotation and the initial phase of the rotation cease to be constants and slowly drift. The location of the center drifts in space, and the initial phase drifts in time. So frequency changes with time, and the drift velocities for the drift in space and time might be predicted as a convolution type integrals of the perturbation with the response functions of the spiral wave. Okay, so the meaning of the response function is you saw this in Dwight's movie. So if the spiral is like that, that is the core. The response function is localized here. Okay, and response function is equal to 0 anywhere far from the core. So if you try to take this integral far from the core, that is 0, velocity generated by perturbation will be 0. You have to affect the core to get the spiral move. Okay? That is generally the idea. And if you have this, you can think about dynamics of spiral waves as particles, more or less in terms of laws of motion. However, and you remember the Newton second law of motion, acceleration, second derivative of the coordinate, is proportional to the force, with mass being a coefficient of proportionality. Yeah? Newton wrote this for conservative media, where conservation law is valid, energy is conserved. And fascinatingly enough, there is another law, Archimedes, before Christ. Okay, he formulated a law of motion for velocity in dissipative media. So if the media is dissipative, there is no conservation of energy. Like in excitable media, action potential is generated by each cell, okay, locally. So, and then it dissipates, and then it takes energy to regenerate again. Okay, there it will be velocity. Velocity is proportional to the perturbation, with the response functions serving as coefficient for proportionality coefficient. Okay, so that is the equivalent. Newton law, conservative media; Archimedean law, dissipative media, hard tissue. Okay, that is the role of the response functions. If you know the response functions and you know what is the perturbation, you can predict and calculate the drift of re-entry. So where take the response functions from? That is quite a difficult problem, but we managed to calculate the response functions for spiral waves in a set of popular excitation kinetics models. So here are spiral wave components and corresponding temporal and spatial response functions. In Fitzhugh-Nagumo, the same components for spiral wave solution in Berkeley model with localized response functions. Regonator BZ reaction model, components of the spiral with localized response functions, and even in Bieler-Reuter, these are components of the spiral wave of re-entry corresponding to the components of the Bieler-Reuter model with corresponding localized response functions for each component. So if you have this, you can predict spiral wave re-entry dynamics in this model due to any perturbation. Okay? So, because the theory is linear, the superposition principle is valid. So if you have more than one perturbation, each perturbation will give its own input, and the specific force for each perturbation can be calculated with the response functions of the spiral. Okay, so again, superposition of the forces gives you the resulting drift velocity. Now, is it applicable to cardiac applications? And ischemic reperfusion re-entry. Abnormal electrical activity from ischemic boundary is one of major causes of ischemic reperfusion arrhythmia. So re-entry is generated from the ischemic boundary sandwich between an intact healthy tissue and the infarcted zone where the cells are decoupled and suppressed excitability. The cells in the border zone may become spontaneously active due to calcium overload or noradrenaline release, and it gets more complicated because of the reperfusion. The boundary zone moves in space, okay, it kind of goes down in this particular slab. So what are the forces, what are the perturbations imposed by the ischemic border zone on emergent reentry in the vicinity of the ischemic border zone? And these are especially random heterogeneity of excitability of cells in the healthy tissue, in the recovered tissue, and then moving gradients of the diffusivity and excitability alpha. So they are moving because of the reperfusion. Yeah. Note here that this model was done with biliary kinetics, and there the alterations in the excitability was due to the suppression of IK1 potassium rectifier current. So what we have? Gamma D force due to gradient of diffusivity, gamma alpha force due to gradient of excitability, gamma kappa force due to the curvature of the filament when it gets into the recovered tissue, and this force gives, the real part of this force, B2, gives the filament tension coefficient. There also will be the pinning force, central force caused by localized inhomogeneities in the recovered tissue. Okay. Nice thing about these forces is that actually the theory predicts that gamma D, force due to gradient of the diffusivity, is equal to minus gamma kappa. So if you calculate one, you immediately get another. So having all these, which gives us perturbations, and having the response functions for biliary kinetics, we can actually calculate the specific forces. We can predict them with the theory, what this will be. So gamma alpha, that is the force due to gradient of excitability, is negative in all considered range of basal excitability alpha 0. And that means that emergent reentry, if it appears, it will tend to go to the lower excitability area because of the negative force of gradient of excitability. Okay? Gamma kappa has a real part, filament tension, changing sign in the considered range of the basal excitability. So at lower basal excitability, filament tension is negative, expanding filaments. At the high excitability, filament tension is predicted to be positive, contracting filaments, no fibrillation. And you remember that gradient of diffusivity is minus gamma kappa, so at lower excitability, at lower basal excitability, theory predicts that gradient of diffusivity is positive, which means that the emergent spirals will be pushed into the beta-coupled recovered tissue, upper zone, yeah, where there will be negative filament tension, and these vortices will expand into fibrillation. Different scenario at the high excitability is predicted. Here the gamma D, gradient of diffusivity force, is negative, which means the gradient of diffusivity moving towards an infarcted area will drag the emergent reentry towards less coupled, negative gradient of diffusivity, less coupled infarcted area. Okay? And even those reentry which somehow get pinned in the healthy area and removed from the moving boundary, they will collapse because there is positive filament tension there. Okay? So you can say fibrillation here, healthy recovery here, depending on the basal excitability. What chances spirals, emergent from randomly from the moving boundary zone have to pin to the localized inhomogeneities in the healthy tissue? The central force caused by localized inhomogeneity or excitability is negative in the whole range of the basal excitability, so it's negative force, which means that the localized inhomogeneities with lowered excitability will be attractive, and localized inhomogeneities with elevated excitability, elevated against the basal excitability of the tissue, these will be repelling. They will push out the reentries. Okay, so and here, however, well-arranged couple of repelling excitability can still block reentry and keep it in the healthy tissue. So, for example, here, the reentry trajectory comes to repelling inhomogeneity, localized inhomogeneity, and it would like, you just see the phase portrait of the velocity field. It would like to go around it, but it cannot, because there is one more repelling inhomogeneity. Two repelling inhomogeneity will block movement of reentry. And that is just how it goes, transient pinning around repelling inhomogeneity, single one, and that is true attractive inhomogeneity, so spiral goes to it and pins to it. Okay, so pinning to attractive localized inhomogeneity or block by two repelling inhomogeneities. Okay. What about the speed of reperfusion? In the higher basal excitability tissue, spiral probability to escape into the healthy tissue will depend on the reperfusion speed. So if the reperfusion is very slow, you remember at high basal excitability, the border zone just drags emergent spirals towards the infarcted area. And if this reperfusion goes very slow, it will allow the border zone to drag the spirals with the moving border zone to the infarcted area and healthy recovery. Yeah? If reperfusion is fast enough, again, there will be no reentry because they will not have time to develop. There will be a vulnerable window for the speed when the speed of reperfusion is higher than the drift of the border zone, but lower than the conduction velocity. And in this window of reperfusion speed, spiral may get detached from the border zone and remain in the healthy tissue being pinned or blocked by two repelling inhomogeneities. Okay, so these are predictions of the theory. Now we can check it in the simulation, and actually that is complete confirmation. So low excitability, negative filament tension, emergent spiral gets pinned in the healthy tissue and develops in macro reentry fibrillation, and lower, higher excitability, slow reperfusion, healthy recovery. Okay, now with recent advances in heart anatomy imaging, allow to see reentry dynamics in realistic anatomy settings. So the heart is not square anymore, and apart from tissue inhomogeneity, anisotropy, irregular boundaries, and so on, it might also have varying thickness of the wall. Yeah. And these may vary from one species to another, from atrial to ventricles and so on. So I hope you start feeling that actually cardiac simulations are intrinsically modular. Because you need to combine, to extract and replace different cell excitation models, different anatomy settings, different inhomogeneity settings, scar settings, and so on. So while the complexity of the problem and the corresponding complexity of software development far exceeds the software development skills of a biologist. So to address the needs, we developed a software package called BeatBox, which includes a repository of cell kinetics models with built-in script interpreter, and also simplified tissue models, 1D, 2D, sheet, slab of tissue, and also we started collection of realistic anatomy repository. Okay, there are solvers. Currently, it's finite difference-based solvers. However, the philosophy of the software allows to include finite elements just as well. Okay, you just need to address the interface between the module, the software modules, and you can run your finite element solver in BeatBox just as well. And then the output and visualization. The nice, I hope, the nice thing about it is that the code BeatBox can be run uniformly, both on sequential processor, just on one processor, or on a cluster parallel processors. For the user, what is needed is just a script which defines parameters of the medium, geometry. Here it's rabbit realistic geometry ventricles. Then cell kinetics you call Fitzhugh-Nagumo cubicle with particular set of parameters. You define, is it going to be isotropic or anisotropic conduction? Then you define what forces you would like to apply on it. Okay, and then you set up where you would like to have your output for post-visualization or whatever you would like to do about it. And after you've got this script, if that is just small model, so not big tissue size, not many nodes, and small cell model like Fitzhugh-Nagumo, you can run it sequentially. Or if it's a big model, you can change from Fitzhugh-Nagumo to Court-Munch or Tentusha. You can change to human atrium or don't dare to mention human ventricles, which will not be able to run on a desktop or laptop. You will have to run it on a national supercomputer and use a message passing interface, distributed memory configuration for the hardware. But for the user, it is still the same script. It's all hidden from biologist or physiologist who runs it. Yeah. So what we did, just as an example, we managed to get our hands on a human atrium from Karlsruhe by Gunnar Simon. So we incorporated the data exactly as it was given to us, regular Cartesian coordinates box with 1/3 of millimeter discretization. We used explicit Euler time step and time, second order approximation of Laplacian, Neumann boundary condition on a regular boundary. Another convenient thing of BeatBox is that there you can use phase distribution method to put your reentry at exact location you would like it to be. It's not S1, S2, which can result in any location more or less, yeah, or cross-field stimulation. You can just artificially put reentry where you want it to be. Yes, because that was quite a big model, we used MPI high-performance computing. So speaking about now features of the anatomy, in atria, I'm sure you can all recognize crista terminalis pectinate muscles in any orientation, yeah? So now we run simulations and we observed different trajectories depending on the chirality of the spiral, clockwise, anti-clockwise, and depending where it was initiated and where it ended up pinned. These simulations, it was anisotropic simulations. There was no fiber orientation, there was no inhomogeneities, so all these trajectories resulted just from pure anatomy, geometry of the atrium. And strangely enough, whatever the model we used, was it Court-Manche or Fitzhugh-Nagumo, the trajectories were more or less the same. So trajectories 1 and 2, 1 and 2 here, kind of probably complex anatomy, not going too far, God knows what's going on there. Trajectories, another simulation, 3, 5. Trajectory number 3, that is from here to there, something, or other way around, and 5 is coming, actually attracting to the opening, pinning to the atrioventricular opening, this big shade here, because that is from epicardial translucent view, and the atrioventricular opening is on the back side, okay? So trajectory number 5 is actually pinning to the AV opening, AV ring. And again, it looked like the trajectories are the same regardless of the cell kinetics. And that one, trajectory number 9, for anti-clockwise spiral, anti-clockwise reentry, was particularly fascinating because initiated in the entrance to the pectinate muscles, it nicely went along the pectinate muscles and pinned to the junction between the crista terminalis and the PM. At this point, when we saw it first time, we were really puzzled. What is it? Is it artifact of the simulation? Or is it really anatomy playing? By that time, we knew about 2 papers reported by UCLA group. One was 1998 and another one was 2012. In their specimen, an experiment, which contained pectinate muscles with crista terminalis junction, they observed propensity of initiated cardiac reentry to pin to the junction with crista terminalis. But this was just an observation, and for them, they reported it. But again, was it one-off, or was it regularity? So still, we observe the same in the simulation. In realistic anatomies, can we rely on it? And here you can see nicely Court-Manche model, very smooth drift pinning. So what is here? Is it the ridge and ditch structures? So if you look at pectinate muscles, these are ditches and ridges on the endocardial surface of the atria. What if we just simulate a trivial ridge? Will it get the same result? Will it transition to the pinning? So here, set of simulations. First, Court-Manche simulation. Initiation of the spiral close to the atrioventricular opening. Here you can see the core of the spiral. Court-Manche model, and it actually doesn't go there. Can you see the flickering? Because the output is stroboscopic, so one image per rotation. You can see it as firmly fixed there, but that is pinning to the atrioventricular opening. And only this flickering here says, yes, that it's movie running. What if we initiate spiral at the same position, but Fitzhugh-Nagumo, isotropic conduction, same outcome, different wavelength, different kinetics, that is just caricature. So it's definitely anatomy, attraction. Now, if we initiate spiral cold march at the entrance to pectinate muscles, counterclockwise, that is what I showed you, pinning to the junction. What if we do the same with Fitzhugh-Nagumo? A little bit different, but you can still say that spinning to the same, more or less the same junction. Okay? Probably the different character here, it's kind of orbiting, dancing around on top of pinning due to the different wavelength. And what if we switch on anisotropy now? We can do it separately in the simulation, okay? So initiation of the spiral at the entrance, anisotropic conduction, and it pins to the junction so fast you hardly can see the time. And what about Fitzhugh-Nagumo anisotropic? A little bit higher, kind of, but pins to crista terminalis. So after that, the suspicion that actually it was anatomy play here, and the anisotropy, anatomical anisotropy, only speeds up the evolution of the reentry, was really strong. So we tried to see it in simplified geometry, and indeed for the ridge, spiral, depending on where you initiate it with respect to the width of the ridge, going up or going down. For the ditch, again, depending where with respect to the ditch you initiate it, it might go up or down. Can we consider interaction with this fluctuation of thickness as perturbation on the spiral and try to describe it with our asymptotic theory? So that is anatomical force imposed on cardiac reentry. And here you can see a really paradoxic example. You remember if reentry rotating around the filament has positive filament tension, that in a wedge, so the reentry will go due to contraction of the filament from thicker area to thinner area, okay? That is for positive filament tension. For negative filament tension, it will expand to the other side. However, here, that is Fitzhugh-Nagumo. And for the Fitzhugh-Nagumo, we know that a particular set of parameters where the filament tension is positive. So positive filament tension reentry initiated gets attracted to the thicker region. So it's not filament tension. It's anatomy step playing role here. So it positive filament tension reentry gets attracted to the thicker side of the step and then drifts along it. Okay, and the theory predicted that actually the speed of the drift will be proportional to the logarithm of the size of the step. Okay, and also, so knowing the response functions in Fitzhugh-Nagumo and in oreganator model, we can compute the specific forces for the interaction with the step. And for these specific forces, the real part will predict the distance from the step for this stable trajectory, while the imaginary part, Sy, will predict the speed of drift along this along the step. And that is in very good quantitative agreement with 2D and 3D simulations, so predictions of the distance and the speed, and the same for oreganator model. So if you have clockwise reentry, it will go upwards. This is a prediction for counterclockwise reentry, so negative speed, it will go downwards. Okay? And the same for oreganator. If there is a ditch or ridge, it means there are two steps. So superposition of two forces from each bank of the ridge, depending on the width of the ridge or ditch, will produce the resulting force with one stable root, a particular distance where a spiral will settle down, and two unstable ones. For critical width of the ditch or ridge, there might be just one root, and for this root, okay, the longitudinal velocity is also equal to 0. So there in the ditch, the reentry just will stay in one place and don't go anywhere. Okay? If the ditch has a cuneiform banks, yeah? So what will happen? The reentry initiated at the narrow part will start drifting towards the critical width, where it will not stop as it should have, because the wedge effect of the cuneiform banks do not compensate exactly. So instead of complete stop, it will just slow down at critical width, like here, and then when it gets further, it will get to one or another bank, depending which side is stable. And then, so from physiology point of view, you will see this area as a transient pinning for no particular reason. However, the reason is there. These are two forces imposed by the banks of the ditch. If there is localized either bulge in the tissue or depression in the tissue, depression is particularly important if you think about ablation and traveling hand. Just a little bit of electrode, not completely kind of perforating, just a little bit, and you've got the depression, which will serve as either attraction or repellent for reentry. And again, the theory predicts the distance at which there will be orbiting trajectory and the speed for orbiting. And again, it's in a good quantitative agreement with 2D and 3D simulations. To appreciate fascinating effects of these theory predictions, so this was done theoretically. Before we submitted the paper to Physiology Letters about this new phenomenon that alteration of the thickness of the layer might affect the dynamics of the reentry, we put our paper into Arxiv, and immediately we've got an email from Florida University, State University, Professor Oliver Steinbock, Department of Chemistry. Professor Steinbock specializes in BZ reaction. So accidentally, simultaneously with our theoretic and results and simulations, they were playing with BZ jelly reaction in a petri dish. And what they found, if you initiate reentry in a petri dish in this reaction, there is no structure. But you take a glass rod, yeah, and you dip it a little bit in the vicinity of the core of the spiral. So for the layer, that means depression in the layer of the reaction. And the spiral get pins to this tip of the rod, and you can drag it. You can write with it. And that was absolutely fascinating result. So now I'm ready to give you the conclusion. Cardiac reentry wave-particle duality explains origin of reperfusion arrhythmias as well as interaction with fine anatomical features. Speaking about reperfusion, development of reperfusion arrhythmias seems to be due to combination of basal excitability and the speed of reperfusion. It should be either very slow or fast enough not to allow to result in defibrillation, given the basal excitability high enough. Okay, the anatomically realistic simulations confirm, reported in the experiment, cardiac reentry propensity to pin to PM crista terminalis junction, and here you can check the references to the papers. Reentry's drift and pinning to small thickness features is distinct from and not reducible to previously known filament tension or curvature-induced drift, nor to a parametric inhomogeneity, nor anisotropy. Drift and pinning to small thickness steps, confirmed by asymptotic theory, as well as I said, now it's published in BZ experiment, and I believe it will have quite important implications for smooth control of cardiac reentry, in particular for ICDs, ablation, because ablation will result inevitably in ditches, depressions, and depending on the location and the combination of the fine anatomical features and these introduced by ablation, ditches, ridges, and other damages, the outcome might be completely different. And as well as for other applications. So that's all I wanted to tell. I'm open, yes, so finally, acknowledgement to all my colleagues. And yeah, any questions?
Irina, that's a very nice talk. Just wanted to go back to the region of acute ischemia that you're talking about.
Mm-hmm.
There you simply just modified excitability alone. Is there any change?
And diffusivity.
Sorry?
Excitability and diffusivity.
Yeah, so in terms of the nature of the activation, I mean, that led to alterations both in the, diffusibility.
IK1. Sorry, I interrupted. Yes, please finish. So,
yes, so
excitability.
What I'm going back to is that characteristically what happens around the area of ischemia is you're getting slow velocity, obviously, which is reflects a change in excitability. You're also getting alterations in the duration of action potential. Did you get both of those things in the model or not? I mean, I don't think it will.
Okay.
I'm just interested to see how.
So I think this can answer your question.
So you don't have the.
So IK1 was modeled. The excitability was modeled as suppression of.
Okay. So you changed IK1?
Yes.
Okay. Which is the. Now that IK1 then was that that affects your sodium channel as well as your duration of action, potential duration.
Yes.
Okay.
Yes. Yeah.
Okay. That's really the question I was asking. So that's fine. Yeah.
Okay.
So with your studies on the changes in thickness and the spiral wave, these were all abrupt changes in the thickness of the tissue.
In simplistic geometries, yes, but in realistic it was not abrupt. It was how it...
So even the rod in the
rod was abrupt, yes.
It's abrupt. Just wondering how it changes, so theoretically what the difference is if there are smoother transitions between different...
I think it will depend. You need really a step. It might be smooth step. If you have kind of gradient, probably it will be rather due to filament tension.
So
Play, not interaction.
About the application to ablation then is if there are sharp edges, then that's maybe your problem.
Exactly. Yeah.
If that is smoother, then perhaps it doesn't contribute in the same way.
I would say it might, because it will depend on the width of your electrode and the shape of your electrode.
So you could start to think about causing changes in such a way that you minimise any effects that you might have.
there will always be the interplay where you, yes. I don't think I can only speculate at this point. I can only speculate at this point. Obviously, the theory is for the sharp ditches and ridges. That is how it was done. In realistic setting, I don't know, but having intuition, you can see it in simulation. Yes.
It would be fairly easy to look at Greg's question. Sorry, I'm an ablationist.
Oh, okay. Yes.
And the cavo tricuspid bismuth can be very smooth,
Mm-hmm.
can be very ridged as you've been describing. And there's quite a number of clinical studies where they've looked at anatomy and outcomes, but not a lot of studies in terms of looking at the electrophysiology of the isthmus. So it'd be a very interesting area to think about, depending on what Greg's talking about and what you're talking about, to look at the wall thickness
Mm-hmm.
as it applies to that particular area. That's a safer area to ablate than, say, for example, in the atrial appendage, where you've got all these beautiful pectinate muscles
Mm-hmm. Mm-hmm. Mm-hmm.
perforate adjacent to them.
Yes, and this opens the question about locations, the access for the electrodes. That is another technological thing where you can get it in the simulation, but you still have to optimize it in real heart. How to get to the area where it really works finely in the simulation. Yeah.
I was going to follow up on Greg's point, and that is the abruptness of your experimental model versus the clinical situation where, for example, the atria stretch with whatever the trigger is, be it fibrotic hypertension, where there's much sphericity of the atrial chain.
And this will affect it, of course.
I was going to ask you to comment on how that might affect some of the...
There is a paper by other people, that is Ghent University, Hans Dirks, Henri Verschelde, maybe Sasha Panfilov, I'm not sure. They have theoretical paper on curvature-induced drift. Curvature, not curvature of the filament, but curvature of the surface, curvature of the space. There also will be drift, and strangely enough, as I said, the vortices, the physics is different. Coming to this probably picture. Yes, I think if you initiate it somewhere here, where there are no particular structures, no vessels, no big openings, nothing. It's just the spherical thing. It seems that the re-entry without additional perturbation just sits there happily, similar to if you observed weather forecast in the vicinity of Japanese islands in the last week. This typhoon sitting there just because of the curvature of the globe until perturbation comes and moves it somewhere. Okay, and in this vicinity, the perturbation might be the signal, the normal signal coming from the sinus node, if it's higher frequency than the re-entry itself, so it can push it, not be suppressed by it. And if it is inflated, kind of hypertrophy or whatever, that means change of the surface. And yeah, it will affect as well, yes.
I think your co-author there, one of them, you probably have met this morning, I'm not sure.
Yes.
Has also, has also found, I guess, pinning of reentrant activity to not just the junction of the pectinate muscles and CT, but also in the left atrium as well to various structures where there are smooth anatomic structures but rapid change. Would that be fair, G-Sharp? Yeah.
Just another question is, I just want to actually notice that actually recently we are also trying to compute the wall thickness, the atria wall thickness. we also control on human atria.
Mm-hmm.
By solving Laplace equation, you do can look at the map, where thick, where the thin region.
Mm-hmm.
But actually, one of the questions I have is actually a print answer is, because you look at the red atria, as you shown here, actually you have some really thin, some really thicker.
Mm-hmm.
But actually, maybe 2/3, not no more. 2/3 are actually rentering drivers actually in the left, actually not in the right atria, right? So, because here you show the right atria, right? Here is have more abundant.
We didn't see much because we probably were so much fascinated by the pectinate muscles. We didn't experiment it much enough with the left atria. However, what we could see, even if you, because there is a lot of structures here in the left appendage. If you initiate a spiral somewhere here in the right atrium, secondary reentry might be generated in the from here, and this is in agreement with the Korean group. They reported that because of the bumps and everything in the left appendage, now they appreciate that this is another source for reentry generation, if not primary, then secondary.
Another question is, when you do ablation, you actually create the fibrosis, right? So we just want to know, when you create, how come we stop the.
It's not exactly. I would like you to discriminate between fibrosis and ablation, because in fibrosis, I'm not physiologist, but my understanding is, in fibrosis the cell may be suppressed, but not completely dead. Okay, so this might be rather heterogeneity, while in ablation, where you actually burn the tissue, that would be, scars.
You're trying to create a very dense scar without any surviving strands.
Yes.
That's where ablation fails, if you leave strands that can regenerate
Mm-hmm.
and conduct. So you're absolutely right, there are different processes, but I think, Jin-Chao, you were talking about where ablation regions might be in the chamber versus where the fibrotic regions might be. And I guess that underpins our lack of understanding of what different disease processes mean for different anatomies, which I guess comes back to this whole business of where scars are in the chambers and why arrhythmias co-localize. So it's a very complex area.
The fundamental question I really love was the approach you guys developed, the phase distribution approach.
Phase distribution.
You actually spend a couple hours, couple days, couple of weeks. Actually, I try to replicate you guys' result. I think for 2D, I think quite easy to do it.
Did you follow the beatbox workshop instructions?
I couldn't get it working.
Okay. Okay.
Yeah, so I tried myself make some my own code. I think it's for 2D, or also for really simplified Sheldon model. For example, like from the common cell model, right? You can really do it. Also for 3D, also for CRM model, you have so many, the sodium channel, all these channels. You want to do that really complicated procedure.
Okay. I would probably show you a bit more, which is unpublished. So I hope you will appreciate it.
I think that's a really great idea, actually. Yeah.
Yes. So this is human fetal, 20 weeks gestation age, ethically sourced, and we got it from Edinburgh. Then Leeds took MRI image from tissue obtained at Edinburgh Human Reproduction Clinic, and using the phase distribution, we can initiate reentry filament in this human fetal heart, and that is raw material. You can see that is the atria, there is the cut probably damaging, and that is ventricle, but still we can play with it, okay? So using phase distribution, we initiate the filament at some particular location, and that is an isotropic conduction. Anisotropy switched off. Yep. and you see it just flies around. In real heart it wouldn't be able to do this because there will be insulation between the atria and ventricles and so on, but here it's just a toy. Okay, now if we do the same location, initiation of re-entry, but now anisotropic conduction switched on, and these the fibers are not formed yet. Well, however, intramural they are formed. So initiate re-entry, and what anisotropy does, gets rid of it. So that was phase distribution, and if you read the beatbox, or not read, but just play, just follow the exercises in beatbox workshop, you will be able to do this. Okay?
On a more general level, I realise being a clinician, I'm at risk of being sounding really silly about this, but one of the things I struggle with, and I think some of my clinical colleagues struggle with all of these lovely animations that all of us here like to look at, is these are simulations of tissue properties, but what's the role of the fluid dynamics in the chamber? Where do you think that affects some of these beautiful simulations?
You mean blood vessels?
Blood's in the chamber.
Blood in the... It's not there yet. Yes, you're right. Yes. You believe it will play a role. It might. But I would say my intuition says, and again, I have to excuse myself, because as you appreciate, my first degree is rocket science, not not physiology. But my intuition says that fluid. No, how to say it? Where to start from? The function of the heart is orchestrated by electrical wave propagation synchronization. So whatever contraction is there, whatever fluid is there, it should not abrupt cardiac excitation, normal synchronization. Okay, so yes, to get complete picture, we need to enrich our model gradually with the blood vessels, with fluid in the chambers, and probably these will somehow change the curvature. In our images, these nice MRI images I show you, the curvature is not right, because you've got post-mortem heart, you put it into the jar, and it takes the form of the jar. Sorry. Yeah? So the curvature is not correct. The curvature with the fluid will be probably different, but the main point is the key to understanding of electrical excitation re-entry is from these simulations. You will get better picture maybe in, I don't know, few years' time.
It's just very interesting to come back to this idea of, for example, left atrial sphericity.
Mm-hmm.
The change in the flow dynamics that occur because of the structural changes may have a very profound influence on, for example, left atrial appendage filling and emptying in an aortic, which no doubt helps contribute to some of the arrhythmias that are generated. And it strikes me that often we're not thinking about fluid dynamics and the impact that has on wall behaviour and as a result on the electrical behaviours. And it's a huge area, and I don't know how clever people are going to actually pull that into helping people like me point a catheters.
I'd say not yet, but it's possible.
Well, on that note of lots of things still to do, it's always interesting, isn't it? This dissection between substrate and theory and the great discussion that comes in.
Yes, yeah.
Thank you very much for listening.
Thank you for the invitation, for having me here.
And if there's anything further we can talk about, or there's some nibbles here, so just join me in thanking Irina.